Imagine a force so powerful that it could rip apart atoms from a distance farther than the moon is from Earth. Now imagine that this force originates from an object so dense that a teaspoon of its material would weigh billions of tons. These are not the imaginings of a science fiction writer but the very real properties of magnetars, the most magnetic objects in the known universe. Magnetars belong to a family of stellar remnants known as neutron stars. Neutron stars are born from the death throes of massive stars. When these stars exhaust their nuclear fuel, they collapse under their own gravity in a spectacular explosion called a supernova. The core of the star, once the engine of nuclear fusion, is crushed into an ultra-dense sphere about 20 kilometers across. This sphere is a neutron star, composed almost entirely of neutrons packed tightly together. Magnetars are neutron stars with an extraordinary twist. They possess magnetic fields trillions of times stronger than those of typical neutron stars. These fields are so intense that they can warp space-time, distort light, and even trigger powerful bursts of energy across the electromagnetic spectrum. From their discovery in the late 20th century, magnetars have captivated astronomers with their extreme properties and enigmatic nature. They offer a glimpse into the universe's most violent and energetic processes. Magnetars are more than just cosmic curiosities. They serve as natural laboratories for studying fundamental physics under conditions impossible to replicate on Earth. By unraveling the mysteries of these extreme objects, we can gain a deeper understanding of the fundamental forces that govern our universe. The birth of a magnetar marks the end of a massive star's life. A star at least 8 times more massive than our Sun exhausts its nuclear fuel. The core, mostly iron, collapses, sending shockwaves outward. This results in a brilliant supernova explosion. The core shrinks to form a neutron star. In rare cases, rapid rotation and a strong magnetic field create a magnetar. Magnetars are defined by their extraordinary magnetic fields, which are trillions of times stronger than the magnetic field of Earth and thousands of times stronger than even typical neutron stars. To put this into perspective, the magnetic field of a magnetar is so intense that it could erase the data on every credit card on Earth from a distance halfway to the moon. These fields are not just powerful, they are also incredibly dynamic. Magnetars experience frequent starquakes, sudden shifts in their crusts caused by the immense stresses exerted by their magnetic fields. These starquakes release vast amounts of energy in the form of gamma rays and X-rays, making magnetars some of the most luminous objects in the universe at these wavelengths. If a magnetar were located a mere 1,000 kilometers from Earth, its magnetic field would be strong enough to rip apart our planet's atoms. Fortunately, all known magnetars are located thousands of light-years away, so we are safe from their potentially destructive power. However, their extreme properties provide us with a unique opportunity to study the behavior of matter and energy under the most extreme conditions imaginable. The study of magnetars and their extraordinary magnetic fields pushes the boundaries of our understanding of physics. These objects challenge our theories of how magnetic fields are generated and how matter behaves under extreme conditions, offering a glimpse into a realm where the laws of physics are pushed to their limits. One of the most intriguing questions surrounding magnetars is the origin of their exceptionally strong magnetic fields. While the collapse of a massive star's core naturally amplifies the magnetic field, the fields observed in magnetars are orders of magnitude stronger than what standard models predict. This discrepancy has led to the development of various theories, with the Tayler-Spruit dynamo emerging as a leading explanation. The Tayler-Spruit dynamo proposes that the intense heat and rotation within a newborn neutron star drive turbulent motions in its interior. These turbulent motions, coupled with the star's rapid rotation, create a dynamo effect, similar to the process that generates Earth's magnetic field. However, in the extreme conditions of a neutron star, this dynamo operates with far greater efficiency, amplifying the magnetic field to extraordinary levels. The Tayler-Spruit dynamo model predicts that the strength of the magnetic field generated depends on the star's initial rotation rate and the rate at which the heat generated during its formation is transported outward. This model provides a plausible explanation for the observed range of magnetic field strengths in magnetars and neutron stars. Understanding the Tayler-Spruit dynamo is crucial for unraveling the mysteries of magnetar formation and evolution. By studying these objects, we can test our models of stellar evolution, and gain a deeper understanding of the fundamental